Hello, everyone. Yeah, get settled. So we will start. Yeah, we don't want to delay too much because it's going to be exciting. So you might know who I am. I'm Mindaugas, working here since January, working with LHCb activities in Lithuania. If you haven't heard what LHCb is, the speaker will tell you all about it. First of all, I would like to thank the organizers of this conference. We have to remember that this is primarily done by students, and it really has grown up to be a nice international event broadcasted on our television. It became important in, I don't know, the international scene and so on, and especially for the science that we do, it's really important. So it's really nice to see this grow. I think the testament to this is how good speakers we can invite, basically, and the fact that they come. So now, the next speaker, his name is Chris. I could be introducing Chris for an hour, but you don't want to listen to me introducing Chris for an hour. You want to listen to Chris, believe me. Very shortly, Chris is a professor in the University of Manchester. He has been a spokesperson for the LHCb collaboration in the years, and this is important, 2020 to 2023. Remember what nice years they have been. Managing a collaboration of 1,800, maybe 1,600 people in those days, when everything was shut down, there was lockdown, and there's a multi-million experiment somewhere 100 meters below the surface, and it still needs to be built, still needs to be upgraded, still needs to collect data, and science needs to happen. This monumental task fell on Chris's shoulders, but he managed it brilliantly. And we are very happy to have him here, and it's a huge privilege for me to introduce Chris in Vilnius, Lithuania. And yeah, without further ado, Chris Parks, everyone.
Oh, many thanks for the very kind words, Mindaugas. I'm not sure whether I can live up to them now. But yeah, so I'm going to tell you a little bit today about antimatter and some of the research that we do on the LHCb experiment that's related to antimatter. I'll start with some general introduction, and then a little bit later in the talk, I'll tell you a little bit more specifically about LHCb. So the talk I've called Antimatter Matters. And I start with a few words about my current role. So I recently took over as head of department in Manchester. And in Manchester, we have quite a big physics department associated with 13 Nobel Prize winners. And we have sort of three big areas. Very big activity in astronomy, and particularly radio astronomy with the Jodl Bank Observatory. Many of us might know us, given the building that we're in, because graphene was discovered in Manchester. And we have a very long tradition in particle and nuclear physics, starting with Rutherford splitting the atom and going all the way up to the LHC that I will be telling you about. At the LHC, the LHC is the big collider at CERN. CERN is the world's biggest laboratory for particle physics. Actually has a large number of activities happening at CERN, but the biggest of those is the Large Hadron Collider. And the Large Hadron Collider is run by a set of member states, associate member states, and other states which have cooperation agreements with CERN. And there are 23 member states and 11 associate member states, and Lithuania is one of those associate member states. And the real big goal at CERN is to really try to understand the most fundamental particles and the laws of nature that go together with those. So a few words about Lithuania and CERN. Lithuania signed a cooperation agreement with CERN back in 2004, and it became an associate member of CERN in 2018. Only quite recently, in 2023, there was a 5-year review of the associate membership, and Lithuania is very much working to try to become a full member of CERN. Actually, Lithuania's had quite some involvement for some time. It's been involved in LHC experiments, particularly CMS experiment, and in R&D collaboration since 2007. And as Mindaugas said, it's very recently started activities in LHCb, the experiment that I work in. Okay, and here you see your previous president, I think, visiting CERN. This is Geddes and Mindaugas talking about LHCb. And there's quite some activities now in particle physics in Lithuania. It's really good to see, and I know that soon you'll be having a 4th Lithuanian particle physics conference. Okay, so a few general words about what are these kind of big aims of CERN, what's the sort of big picture of the kinds of things that are trying to be done. The big picture really is trying to understand what the universe is made of at the most fundamental level, and we really try to study these most elementary building blocks of which matter is made, and the forces that understand the forces for their interactions. Atoms are down at the sort of 10 to the minus 10 meters level, nucleus down at sort of 10 to the minus 14, protons inside the nucleus at the 10 to the minus 15 level. But the kinds of particles that we're dealing with are the ones which, as far as we know, are point-like. So particles like the quarks, which are inside the proton, or similarly the electrons. That's one way of thinking about it. Another way of thinking about the same kind of question, really, is what happened at the start of the universe? How did the universe really begin? As you know, that we have this concept of the Big Bang, and our accelerators really give us a way of trying to picture back to the start of the Big Bang. And we try to reproduce the conditions that happened in the Big Bang just a fraction of a second after the Big Bang. And that gives us information about the way these elementary particles interact from our studies, and that tells us about the structure and the evolution of the universe. Okay, so after this very sort of general introduction, I want to say a few words about some of the more specific kinds of results that you might have heard of from the LHCb experiment that'll come up a little bit later in this talk. LHCb has been in the news a fair bit over the last few years, and there's a couple of different areas. One of them is particularly around differences between matter and antimatter, and I'll say something about that. And others are about new types of particles that we have found at the LHCb experiment, and I'll describe those a little bit as well. Okay, so let me start with a little bit of history. Where does the concept of antimatter come from? Well, in the August 1898 edition of Nature, there were 2 letters. The first letter said, there is a live frog that has been taken out of a snake. And you may be interested to hear of another incidence of a frog returning alive from the stomach of a snake. That's not the letter we're interested in. Instead, if you're worried about the snake, worried about the frog, the letter does go on to say that the frog, rather off-color and not very happy-looking, slid out. So at least the frog was safe. And then there's a second letter in the same issue. And that letter was called Potential Matter, a Holiday Dream. And that said, surely there is something wanting in our conception of the universe. We have positive and negative electricity. We have north and south magnetism. What about symmetry between matter and antimatter? And it goes on to speculate in this very hand-waving way, maybe that matter and antimatter could even combine into bodies of small mass. And that happens as well. Particles such as mesons, tetraquarks, and pentaquarks that I'll discuss a little bit later. So very, very speculative, but it's the first mention of the concept of antimatter by indeed one of the first heads of department in Manchester. And it finishes with, "Do dreams ever come true?" Well, hopefully I can tell you a little bit about that. Actually, not much happens for about 30 years or so after that. And then in the early 1930s, people had started to put quantum mechanics and relativity together. And when they did that, they started to come up with equations that had multiple solutions. Okay, so in the simplest case, one could think of an equation, a quadratic-style equation that has two solutions to it, a positive solution and a negative solution. And Dirac, with his equation, posited that these negative energy solutions could correspond to antimatter. Now, nobody had thought of the idea, taken really seriously the idea of antimatter at that point. It was a speculation purely based on the mathematics that was written down. But people then did start to take the idea seriously, and only a year or so afterwards, the positron, the first antiparticle, the antimatter equivalent of the electron, was discovered. Okay, let's go even further back into history, and let's start at the Big Bang. So in the Big Bang, we believe that the production mechanisms the basic production mechanisms would be symmetric. So we would have equal amounts of matter and antimatter produced. So here's our universe at the start of the Big Bang. But we all know now this is not the case. We're all sitting here made out of the same types of matter. If we look astrophysically, we see that all the universe around us, as far as we can see, seems to be made out of matter. So my next section that I want to talk about is a few words about symmetries. So matter and antimatter are really like mirror symmetries of each other. We can have a matter atom that we're used to with a nucleus, and then inside the nucleus we have protons and neutrons, and inside the protons and neutrons we have these quarks. And then we have electrons orbiting around them. Okay, and that's basic constituents of all the matter that we're made of. But we can also have an antimatter version of that, a complete symmetry where we can make atoms which seem to behave exactly the same way as the matter atoms. And in fact, antihydrogen has been made over the last a decade or so at CERN, and tests are done on antihydrogen. And the two appear to be entirely symmetric. So there's a kind of mirror universe between matter and antimatter. And indeed, to go a level deeper, in the standard model of particle physics, which is all the particles that we know about that make up our basic physics, all the fundamental particles are given by this picture here. And the picture has a complete symmetry to it. There are these types of quarks that I've been just mentioning, the up and down ones being the ones inside the proton and the neutron, but there's also more exotic types called charm, strange, top and bottom. And there are leptons. There are particles like the electron and heavier versions of them, and neutral particles that go with those called neutrinos. And this picture, though, has two sides to it. These are the matter particles. These are the antimatter particles. There is a complete symmetry between these fundamental particles, and then at the bottom, we have the particles that carry forces as well. So how did we get there? We started at the Big Bang, and we're now 14 billion years later, and we've gone from a universe which we believe to have equal matter and antimatter, to a universe today which really seems to be highly, highly asymmetric. In fact, the only antimatter that we seem to see today is effectively produced in particle accelerators artificially ourselves, or cosmic versions of the same thing, where a particle is accelerated, has a collision, and produces antiparticles. You can see this, for example, in showers in the atmosphere, where a particle hits the atmosphere, and then you can have antimatter produced. But we don't see any signs of any kind of primordial antimatter, any antimatter actually left over from the Big Bang. So how do you get from a situation which was extremely symmetric to a situation which is highly asymmetric? Well, let's talk a few moments about some symmetries that you can apply to the laws of nature. So there are continuous symmetries that you're probably used to. You know, the laws of physics over here and the laws of physics over here should be the same as each other. I can make, and that actually, there's a theorem called Nerva's theorem, which shows that those sorts of symmetries actually give rise to particular conservation laws. But the ones I want to discuss here are discrete symmetries that you can apply. Okay, so ones which are kind of like mirror symmetries. So the first one is a symmetry of charge. So I can swap my positive and my negative particles. The second one is parity. That's effectively a mirror symmetry. Rather than just a conventional mirror, it's really an inversion through the origin. So you're swapping left with right, up with down, forwards with backwards, an inversion through the origin. That is the parity symmetry. And the third one is the time symmetry, reversing the direction in which a reaction happens, for example, and saying, can I distinguish between those two different directions? So those are the three symmetries, C, P, and T. And all our basic theories, our most fundamental theories, are quantum field theories in particle physics. And all those quantum field theories actually conserve the combined symmetry of acting with C, P, and T. When we're thinking about matter-antimatter swaps, what we're actually doing is we're applying both C and P. We're swapping the charge of the particles and we're inverting through the origin. Okay, and I've got a sort of analogy for that. So here's a picture by M.C. Escher, you might be familiar with, and if you look at that picture, you might see one or two things, right? But let's try and think of it one way. The way I immediately see it today is I can kind of see black birds flying to the left on this image, okay? I'm now going to represent the charge operation, changing particles to antiparticles, by changing all the black parts of the image to white and changing all the white parts of the image to black. Okay, so I'll do that, and I get that picture at the bottom. And now you see that what I see is white birds flying to the left. Okay, so I can clearly distinguish those pictures when I apply the charge symmetry. Let's try applying parity symmetry instead and inverting through the origin in a kind of spatial mirror. So let's do that. Okay, and now I've inverted with P, and indeed I can still very clearly distinguish these pictures, and it looks like I've got white birds flying to the left again. Okay, but what about if I try and do both? So I do both C and P simultaneously, and then I'd get this picture like on the bottom right. At which point, if I look to the top left and the bottom right, these two at first glance look fairly indistinguishable to each other. And this is a pretty good analogy of what happens in the universe when you apply the symmetry of C and P to your equations, to your reactions. And it looks like I've got blackbirds flying to the left and blackbirds flying to the right. In fact, this is an even better analogy, because if you look really carefully at this image, they're not absolutely identical to each other. I don't know, for example, on this river over here, I can fairly clearly see some people rowing along, whereas on this one over here, I can't. So if you look very finely, there are some differences between matter and antimatter, but at first glance, it really looks like they're symmetric. And when the equations were first written down, when people first started to understand that there was this mirror image universe of matter and antimatter, people assumed it would just be completely symmetric, and the equations would be symmetric between matter and antimatter. And in fact, you could write down a standard model of particle physics, a behavior of all the fundamental particles, which was perfectly symmetric between matter and antimatter. However, if you did that, how on earth would we be here? Because we need something that gives some difference between matter and antimatter. Otherwise, we wouldn't be able to get from that symmetric initial condition to the asymmetric universe that we live in, which is matter-dominated today. Okay, so let me talk a little bit about some of the discoveries that have been made about matter-antimatter asymmetries, a bit about the LHC, something about these discoveries, and then I'll finish finally with a few words on sort of everyday applications of antimatter. So first thing is to introduce the Large Hadron Collider. I'm sure many of you have heard of this before, but the Large Hadron Collider, as I said at the start, is the most powerful particle accelerator in the world. It's 27 kilometers in circumference. It's on the French-Swiss border, relatively close to Geneva, and it has 4 large experiments, which are around 100 meters underground. CMS, LHCb, Atlas, and Alice. And each of these experiments specializes in slightly different types of physics that it's studying. The one that I'm going to talk about mainly today is the LHCb experiment. And LHCb particularly specializes in looking at differences between matter and antimatter. So this is the detector. On the left-hand side, you've got a kind of cartoon of it. And on the right-hand side, you've got sort of me and 500 of my closest friends in front of the detector. Actually, we weren't in front of the detector; it's photoshopped. We were taken in a hall on the surface of CERN, because for safety considerations, we can't actually all be 100 meters underground in the pit. In this image, on one very side of the image, actually the pictures are opposite way round. The collisions happen on the very, very right-hand side of this detector here, or in this image here, they happen on the very left-hand side here. So protons that are going around this 27-kilometer ring collide there and produce a spray of the particles that we're interested in, and those particles go through the different pieces of this experiment. And those different pieces of the experiment each allow us to measure different properties of the particles. So each part of the detector is characterizing the particles, a different characteristic of the particles using different technologies. As Mindegaz said in the introduction, we're effectively now in the second phase of the LHCb experiment. We ran the first phase from 2010 through to the end of 2018, and then we shut down and had a major revamp and put in new technology to allow us to study these particles more, to be able to take higher quantities of data and to have higher precision. So the next generation version of the LHCb upgrade was completed last year, in fact. Here are just a couple of images of it. I'll show a little bit more in a moment. This is the magnets. You can see the coils in the magnets here. These are some of the tracking stations. And then the data comes out from this detector and has to be analyzed in large data analysis centers. And we have a large data analysis center on site, which makes the first decisions about which events from these proton-proton collisions we want to keep and which ones we want to throw away. Because we simply cannot store all the data that's coming out. The collisions are happening 40 million times a second, every 25 nanoseconds. This is one of the elements that we built in Manchester, these so-called silicon vertex detectors. Okay, and I want to show you a short video to give you just some kind of idea of the scale of these experiments and the work that went in. So this is just 1 minute about the installation of this new version of LHCb. So the first thing we had to do was we had to remove the previous version of the LHCb experiment, and that took us about 6 months. This is this new data center that I showed you the photograph of earlier going in. Large numbers of optical fibers for the readout of the experiment going in. This is a foil which separates us from the collision point of the LHC going in around the vertex detector. This is the beam pipe in which the protons go, going back into the experiment. Here's some electronics for our detection of muons, or heavy electrons. This is a system that tells us pions and kaons and protons apart from each other, particle identification system. This is our big tracker. This detector is based on scintillating fibers, and it used 11,000 kilometers of scintillating fibers. These are the photon detectors for the other particle identification system. This is the last piece going in, the vertex detector. Yeah, so hopefully that gives you a little bit of idea of the scale of this. It's a huge enterprise. There are, of order 1,500 scientists around the world in about 100 different institutes working on this experiment, all working together, and these components of these detectors were produced all across the world in these institutes and then brought to CERN and installed to make this experiment happen. And then what's the kind of physics that we're trying to do with this? Well, I'll give you one example. So one of the types of matter and antimatter difference that we have seen is something that we discovered in 2019, and that relates to the charm quark. The very first observation of some difference between matter and antimatter actually dates back to the 1960s. With the strange quark, and then in the early 2000s, a matter-antimatter difference was seen involving B quarks, and then in 2019, we saw this in the final other system in which one expects this, and potentially in the standard model, and that is containing the charm quark. So what did we do? Well, effectively, what we did was we analyzed a large amount of data that we'd taken over, roughly a decade. And as the particles pass through this big detector that I showed you, they leave charges, they ionize the detector, and you get hits in the detector. And those points you then join up with computer algorithms, a kind of computer algorithm join the dots, to reconstruct the tracks of where the particles have been. So when you've got the trajectory of these particles, these ones I've colored in red, are pointing back to this point here. And these ones, we believe, come from a particle that contains the charm quark, and this has decayed into these two red particles that we reconstruct here, and they seem to be pointing back to a vertex here. There's another vertex here in blue, which is where we believe the protons and protons originally collided, and lots of these tracks colored in white point back to that because we had lots of tracks produced in the point where the proton-proton collided. So this thing in green here, which we haven't observed directly, but we've observed these tracks and we've observed these tracks, is where we believe the particle containing the charm quark was produced and then flew a few millimeters out before it decayed. Okay, now it's traveling very, very close to the speed of light, so its lifetime is really small, down at 10 to the minus 12 of a second. But because it's traveling so fast, it actually travels a macroscopic distance of a few millimeters, and we can reconstruct that we had that charm quark there. So if you like, our experiment is like a big camera, but a big camera that's taking 40 million photos per second. And we're looking for this type of decay for this particular analysis. And from this 10 years of data, we got 70 million of this type of decay, which we were able to analyze and look at how many of them happened with a particle containing the charm quark and how many happened with a particle containing the antimatter equivalent of the charm quark, the anti-charm quark. And what we saw was there's a difference, but it's a small difference. It's about 1 in 1,000 difference between the behavior of the matter and the antimatter variant. Okay, so this symbolized in this little cartoon here. I've got this particle which contains the charm quark. It decays into two other particles. Those were the red particles that you saw reconstructed on those pictures before. And I compare this in a mirror between the matter and the antimatter variants, and I see just how many of these decays that I observe, and I find that I've got a difference in the number. Whereas if the universe was completely symmetric and the production mechanisms are symmetric, then I expect that I should have equal amounts of both of them produced, and the fact that I don't is showing me there's a fundamental difference between the behavior of matter and antimatter. So we've actually seen a number of these differences. These differences between the behavior of matter and antimatter. This is a different one. This is for one containing the beauty quark, and we compare ones with this so-called B-meson and this anti-B meson, and we look again at how many we have of these types of reactions. And we find that there is a fundamental difference between matter and antimatter. So what do I mean by fundamental? Well, what I mean is that calling something matter and calling something antimatter is not fundamental. It's just a convention. we just decide to label the stuff that we're made of as matter. If we'd been made of antimatter, all our chemistry, all our basic behaviors would have been the same. We would have just called the stuff that we're made of matter, whatever it was. Okay? So that's not fundamental. But this is fundamental because it actually allows you to distinguish between the two types. Okay? So I've got an example for that. Okay, so I'm going to have two virtual volunteers for this. Okay, so my first one is your president, yes, and my second one is your statue of Frank Zappa. Okay, so your president's going to ask this rather technical question, which is: are your electrons the preferred decay state of long-lived kaons? And if he asks that to Frank, and Frank replies, we will know whether Frank's is made out of what we call matter or whether he's made out of what we call antimatter. It actually allows us to fundamentally distinguish between the two. It's not just a convention. Okay. So Frank is going to say yes to this question. So then we'll have the two of them go and shake hands with each other, and we will see what happens. And bang, okay? It turns out that Frank is made out of antimatter. The two shake hands, and when they do so, the matter and antimatter annihilate each other, and we get photons given out, okay? So if you ever want to call up your friendly alien and find out whether or not you should go and meet him, you now know what question you should ask before you go and shake hands with them. Okay, so it sounds, from what I've said, as if we've sort of got an explanation now. We said that we started with a universe which was entirely symmetric between matter and antimatter. We've now seen that we have some experimental proof that there are differences between matter and antimatter. We even have a way to put this into our standard model, our basic theory of particle physics, to put a difference in between matter and antimatter. So it sounds like we're going in the right direction, but there is a problem. When you actually calculate this, it is nowhere near enough. So yes, you can have a difference in the behavior of matter and antimatter. Qualitatively, it sounds like you're going in the right direction, but quantitatively, it does not work. By orders of magnitude, you do not have enough difference between matter and antimatter to explain the universe in which we live. Clearly, there has to be some other source which is giving us matter-antimatter difference, or we wouldn't all be here. We would all have been annihilated into photons. And that is a big open question. And by finding out more about antimatter, it's unlikely that with these quark reactions we will find something which is going to explain the full problem and find a source which is going to give a big enough difference. But if we can make these studies and we can see some deviation from the theory, then it might start to open up a little crack, a point in a direction that will tell us about how matter and antimatter could behave differently. It might even give us ideas about other big puzzles in physics, things such as dark matter, for example, if you've heard of that. In fact, there are some particles in nature which are even weirder that actually can oscillate between being their matter version and their own antimatter version. So there are 4 particles which are combined particles which contain a quark and an antiquark. And these particles containing the quark and the antiquark, these 4 examples, are particles that can actually start off, say in this yellow line here, as a matter version, and then over time, they will oscillate into being their antimatter version and back as a function of time. It's a bit like a coupled pendulum, if you've ever seen one of those, where you can swing one pendulum, and then the other pendulum starts swinging and swings backwards and forwards, and then the first one does. And it oscillates between being matter and antimatter. Okay, so I'm going to try and allow you to listen to an oscillation between matter and antimatter. So what we've done here is we've taken the data we've observed from the LHC of the oscillations between matter and antimatter of these particles, and we've transformed the frequency down into the audible frequency. And there's two particles of these particles that are going to be on this mass spectrum that I'm going to show you. If I can get this to work. I might need a hand, sorry. Thank you. Perfect, okay, great. So we're going to scan over a mass spectrum, and you could at this point hear a frequency, that's an oscillation, and then you could hear an even higher frequency. Okay, so those are auditory version of the oscillations between matter and antimatter. The first one is a particle that oscillates at 80,000 million hertz, a modest 80,000 million hertz, so it's quite a low frequency you could hear. And then the second one is oscillating all the way up at 3 million hertz, obviously very highly transformed so that you could hear them. And indeed, there are these particles of which matter is made out of, like the proton and the neutron, which are quarks combined. And since the 1960s, 1970s, we've known about quite a number of these, and we have a big book called the Particle Data Group where we put all the characteristics of all these particles that we found. And there were basically two types. There's either mesons, which contain a quark and an antiquark, or there's baryons, which contain three quarks together. So the proton and the neutron are examples of baryons, which contain three quarks. Out of these, we can kind of build a periodic table of particle physics of these particles containing the quarks and how they are related to each other, so how they are combined. And that's kind of this image on the left-hand side. Here are some of these baryons, these ones containing three quarks. The proton and the neutron are up at the top here, and here are other more exotic baryons, which combined contain these three quarks. But what we found at the LHC in the last few years, and another experiment also, is that actually you can make particles not just out of 3 and 2, as we've known for a long time, but you can also make new particles out of combining sets of 4 or 5 quarks together, so known as tetraquarks and pentaquarks. We found quite a significant number of these now. In fact, we're even starting to build up the very first indications of, like I showed you before, this kind of periodic table of these tetraquarks and pentaquarks, of how these particles are related to each other. But there's still quite a lot we don't know about these. We don't really know how the quarks are bound together. You know, in this example at the top, I've got a 5-quark system, a pentaquark. And it could be that those 5 quarks are tightly bound together, or it could be that those 5 quarks actually are kind of like a molecular analogy. It's more like a baryon plus a meson joined together, and the pentaquark is more like you know, at this nuclear particle level is kind of like a molecule built out of those. So we're trying to learn more about actually how the structure of these exists for both the pentaquarks and the tetraquarks. Quite often in sort of media interviews and things, people start interviews by saying, so the LHC's discovered one particle. It's like, no, let's start again. The LHC's actually discovered a very large number of particles. We're up at 72 new hadrons at the LHC. Discovered one amazing paradigm-shifting new particle called the Higgs boson, a fundamental particle. But the total number of particles discovered is actually very large. Quite a few of these are conventional ones, like these mesons and baryons that I've been discussing. But there are actually over 20 of these, which are these new states of matter, tetraquarks and pentaquarks, that we've discovered in the last 5 to 10 years. OK. So let me say a few words before I finish about where we go next. Well, for the LHCb experiment, we have just put the second generation version in, as I showed you. And that second generation version is going to run for about 10 years or so. And then in the 2030s, we will put a third generation version of the LHCb experiment in. And that will run again for about another decade into the 2040s. And the other experiments at the LHC are doing similar things. The experiments Atlas and CMS, they are having major upgrades that will happen in the second half of this decade. The LHC overall will go to a phase which is known as the high luminosity LHC. So this will increase the rate at which collisions happen. Well, the beam crossings still happen at the same rate, but every time the beams cross, you get more collisions between protons happening. So this high luminosity LHC will start in the second half of the decade, and there's lots of work at the moment on the construction of Atlas and CMS experiments to be ready for this phase. And we're operating now, taking more data. We will then shut down, and we will have this upgrade. But we're already thinking about what will happen beyond that. These projects in particle physics, extremely large scale, international collaborations between many, many countries, as I've shown you. And they're very long time scale projects given their physically large scale and the large number of people involved. So at the moment we have the LHC, which is 27 kilometers. And we have a proposal which we're doing a feasibility study for at the moment of a future circular collider, which would be 91 kilometers. And the LHC would be a feed-in to that future circular collider. So in fact, CERN does this a lot. The previous accelerators are used as the injection chain going into the next large projects. So this FCC project would be a project for starting in the 2040s. And potentially having two different phases. One in which we would collide electrons and positrons, and a second phase in which we would collide protons and protons, like we do at the LHC, but at much higher energies. And those two projects will actually take us out till the end of the century. So this is really long-scale planning. Okay, before I finish, I wanted to say, I didn't want to leave you with the idea that antimatter is something completely remote, that antimatter is something that you never come across. Actually, antimatter does have everyday applications. The largest application is something called positron emission tomography, or PET scans. Okay, so some of you may have had a PET scan or know somebody who's had a PET scan. And the idea in a PET scan is that you drink a liquid, and that liquid contains substances which are then preferentially taken up, say, by a cancerous tumor you might have. And that cancerous tumor would consume some of the substances in that liquid. And inside that liquid, there's something which gives out positrons, the antimatter equivalent of electrons. And those positrons then annihilate with electrons, matter and antimatter joining together, which gives you photons, gives you the particles of light, or gamma rays, as we call them, at higher energy. And those photons then come out and are detected by sets of detectors around the outside. So that's the biggest application of antimatter, which is used in hospitals worldwide. There are other applications of the same kind of technology. For example, the same kinds of things is used for tracking in fluids. People have done work on trying to improve washing machines by putting the same kinds of liquids in and looking at how the fluids circulate inside. Okay, and finally, I want to say that it really is extremely common. I don't know if anybody had a banana for lunch, but if you did, and during the time that I've been speaking, your banana has probably emitted a positron or two. Bananas are quite high in an isotope of potassium. An isotope that is a beta plus emitter emits positrons. And in fact, you emit antimatter. We also contain isotopes that emit antimatter. So yes, in our everyday life, in our everyday existence, we don't come across antimatter so much, but actually it does have everyday repercussions, and it can be detected in an everyday level. Okay, so let me come to my summary. Hopefully, a few messages that you might take away from this. Antimatter is almost symmetric with matter. We originally thought that it really was entirely symmetric with matter. But now we know and experimentally can see some differences between the behavior of matter and antimatter. We have this qualitative explanation of the fact that there is a difference between matter and antimatter, which could explain the matter-antimatter asymmetry in the universe, but quantitatively it does not work. We're just not seeing differences big enough to explain how we got from the symmetric matter-antimatter situation at the start of the Big Bang to the situation that we're in now. We have found new types of matter and antimatter difference at the Large Hadron Collider over the last few years. And we have also found new types of matter, these ones called pentaquarks and tetraquarks. And finally, you all emit antimatter. Okay, thanks very much.
Yes. Thanks, Chris, for this amazing presentation. It was really, really nice to hear it. After my 10 years on and off at CERN, I still learn something new from Chris every day. Let's say I haven't heard C meson oscillation in sound, never in my life. So that's a new thing. That's interesting. Okay, I'm sure you will have questions. So let's start with questions from the audience. Yes, Tadas. Yeah, catch the cube, Tadas. Yeah?
Is it? Yes. Is it? Yes. So my question is, are we sure that during Big Bang we have complete symmetry between antimatter and matter?
Yes, we're fairly sure, actually. The basic production mechanisms are ones which really are still symmetric between matter and antimatter. There are four forces of nature, right? Gravity is not relevant for these processes. So there's electromagnetism, the strong force, and the weak nuclear force. And the electromagnetic force and the strong nuclear force both appear to be entirely symmetric, as far as we can tell, between matter and antimatter. The one that isn't is the weak nuclear decay. And those examples that I gave you from are all the ones which are going through charged weak nuclear decays, where quarks are changing their type, emitting W-bosons. And it's that nuclear decay process which is giving us the asymmetry that we're seeing.
Okay, before we go to the next question, I have to remind you, there will be an important part after Chris's talk. Ramūnas, the director of Consortium for Particle Physics, will introduce how you can join actually LHCb and other CERN-related activities in Lithuania, Vilnius, which is important to listen, so don't run away. And let's go to the next question. We have this problem in Lithuania. People are shy to ask questions. Ahead.
Yes, so yeah, working. So you spoke about CP transitions. Any theoretical works on CT or PT transitions?
Yes, actually, a good question. So you're absolutely right. So I told you that C, P, and T combined are conserved, and I told you that CP is broken. So actually, that means that T is broken. You can imagine a reaction of the form particle A and B interact and go to particles C and D. And I can imagine playing that movie backwards, if you like, and looking at the reaction particles C and D goes to particles A and B. Okay? And what you find is that there are examples in which those do not happen at the same rate as each other. So there is, in fact, time dilation. The examples that I showed today are probably easiest thought of in terms of CP violation, but there are processes which really have been analyzed in terms of T violation and shown really directly to violate T.
So my question is, are we sure that there is rather no antimatter in the universe? How do we know that? And if there was a galaxy made of antimatter, how could we distinguish it from the matter one?
Thanks. No, that's a very good question as well. The base assumption I'll start with first is that you would produce matter and antimatter in equal amounts. And that matter and antimatter that you produce, you assume would be fairly homogeneously distributed. Okay? If it's homogeneously distributed, then of course it would potentially annihilate out. And we believe, in fact, that it did mostly annihilate out because the universe is largely made of photons, actually. And we're just the little bit that's left over when it almost entirely cancelled out, but didn't exactly cancel out. Okay. But let's go with your idea for a moment, and let's imagine that somehow there was some extra force that we don't know about that somehow decided to separate matter and antimatter out, and that some part of the universe would therefore become made of antimatter, and some part of the universe would be made of matter. Okay. Now, if that was to happen, then you would obviously have some junction point. The junction point, you would have annihilation between matter and antimatter, and from that point in the sky, you would have high-energy gamma rays being emitted. So indeed, there are experiments, including effectively like kind of space-based particle physics experiments, if you like, satellites that look for these gamma rays. And we see, to date, no significant evidence of any such thing occurring. So that's true. And it's also, as I said, you'd need also a mechanism as to what caused it to happen, which we don't have as well. That's a good question. Thanks.
Okay, please.
So I have a question about antimatter disappearing, sort of, or the difference in matter and antimatter. So are there any theories or thoughts of what might be happening, what would be the potential physics or the potential pathway towards the solution? Because, well, when it's unknown, there should be in physics something that would lead towards that.
Yes, absolutely. So a large number of new physics theories that you write down, which then posit particles from beyond the standard model ones that I showed in the talk, would violate CP symmetry. So often when you add a new particle into your theory, it adds a new source of matter-antimatter asymmetry. And in fact, in many cases, you have to tune the theory in order to not violate things that we already know from the experiments of matter-antimatter difference. So one great thing would be, if we did start to see just some small differences that didn't match up with the theory, whether that actually could open up a window not just to solving this problem, but to solving other problems that that new physics theory was potentially trying to solve as well. That would really be wonderful if actually it turned out that this puzzle of matter and antimatter asymmetry was related to other puzzles in the universe as well. One other thing I will say is that I discussed today the quark sector. There's also the leptons as well. Okay, and the leptons, the charged leptons and the neutrinos, they are another potential source of matter-antimatter asymmetry. Experiments with neutrinos are very difficult, but there are large experiments ongoing at the moment and will be starting up that are trying to make CP studies on neutrinos also. And given that CP, as we've seen, exists in the quark sector, it's quite likely that CP violation can exist in the neutrino sector as well, but we haven't yet discovered that.
Yes, a few more questions we have time for, so please. Yeah, just throw it and let's see what happens.
Thank you for a nice talk. My question is, why did it take so long to discover CP violation in its C quarks? I mean, I guess it's just the smaller amount of violation, but why is that?
Yeah, no, that's a good question. In a way, nature was very kind to us as to why the first discovery of CP violation happened already in the 1960s. It turns out that the CP violation that happens in the strange quark, there are a particle called the K0, and it exists in two states, one which decays rather quickly and one which lasts much longer. And that made, because these are really macroscopic times, or at least on the particle physics scale, you could really build an experiment where you had this particle just fly for quite a long distance. And after it had flown for a long distance, then you knew you had one of these particular states, and then you could measure that, and you could see a difference between a CP violation. So it was a fortunate experimental circumstance that nature had given us, that with relatively simple technology compared with what we have now, we could already find this CP violation back in the 1960s, and it was completely unexpected when it was found. It really was a surprise. In next complexity, experiments were built to try to find this in the B quark system. And at that point, there was already a prediction about how this should behave if it was embedded inside our standard model of particle physics. And those experiments that found the CP violation in the early 2000s then showed that actually the standard model picture did work of how matter-antimatter difference was put into our theory. Okay? It doesn't explain the matter-antimatter asymmetry in the universe, but it is self-consistent inside the theory. The charm quark one, even more difficult, because you need to have extremely large rates of charm quarks produced in order to be able to do this. I showed you that the analysis here was analyzing tens of millions of events in order to find this. And the LHC is the first facility that's been able to produce that kinds of rates of particles to be able to probe down at the level to be able to see this difference.
Okay, thank you.
Thank you. Yeah, we have time for one more probably, so let's get back.
Okay, maybe my question is slightly at the edge of this topic, but you told that the matter at the Big Bang was homogeneous, and nowadays the universe is not homogeneous. So why we can assume that?
Okay. No, that's so you're absolutely right. So there are lots of theories in astrophysics about how the universe evolved. How much detail to go into, but there was an early period in the universe we believe called a period called inflation, where things hugely expanded and where very small differences in clumping became highly magnified. And then you go through stages of all the formation of the large-scale structures in the universe. And the gravitational attractions then later in the universe then amplify these differences. Mm-hmm. And you end up with structures that we have today. And people develop models where they put in the physics that we know, and they try to run through the birth of the universe and the creation of this structure to try to see whether these models actually fit with the large-scale structures that we actually observe today.
Okay, so matter was not homogeneous, so this assumption that matter and antimatter should be homogeneous set in space, it's...
Yes, but in what... Oh, thank you. In what our colleague over there was talking about, you really needed a separation between matter and antimatter. Mm-hmm. You know, you really needed two distinct regions. As said, we do not have a mechanism that would force matter mm-hmm. and antimatter away from each other. And even if that was to happen, we have no evidence that it actually does, because we don't see anything from a junction.
Okay, thanks.
Okay. Thanks very much for all the questions. It's been amazing. Thanks, Chris, again for amazing presentation and your answers. It's really, really cool. Now I invite the director of Lithuanian Consortium for Particle Physics, Ramūnas Aleksiūnas, to talk about how you can get into this space and how CERN is done in Lithuania so far.
Good afternoon. I'll be brief. I want to tell, as Mindaugas already introduced, the only and sole mission is to show that there are more than one way for you to join CERN, being in Lithuania. And I just want to show you how and what you can do in order to contribute. So my job is to talk about Lithuanian Consortium of Particle Physics. It sounds very dull, I understand that, very bureaucratic, but I'll try to show it what it does and how can it contribute.